Okay, welcome everyone to the Friday seminar. I'm excited to have Prafulla Dhariwal visiting us. He's a research scientist at OpenAI, leading work on generative models under the guidance of Ilya Sutskever. He obtained his undergrad degree from MIT in 2017 with a double major in computer science and mathematics. His work focuses on modeling high-dimensional data while preserving fidelity and diversity. And some of his top hits include works like GLOW, which is a normalizing flow generating high-resolution images with fast sampling. Prafulla is here to present his most recent work, Jukebox, which is a neural network that generates music via raw audio. And this topic is very near to my heart. My very first machine learning project was music modeling with RNNs in 2011, and it was supervised by Ilya Sutskever. So now, 9 years later, I'm just totally stunned at the progress and the quality of music generated by the models that Prafulla developed. So I'm super excited to hear more about the details. And if you'd like to chat with him, please email him at the email that's posted in the chat. He's kindly made some time to meet with people here at Vector today. So take it away, Prafulla. Thank you.
Thanks a lot, Chris. That was an amazing intro. And thanks for having me here today. I'm gonna start screen sharing. So, okay. Can you all see the screen?
Yes.
Okay, cool. Let me set this up. So, hi everyone. My name is Prafulla, and as Chris said, I'm a researcher at OpenAI working on generative models. And today, I'll be talking to you about generating music using neural networks. And before I jump into our talk, let's first listen to some music from our models. What you're about to hear has been generated completely from our models. And I'll just play it out for you first.
It's Christmas time and you know what that means. Oh, it's hot tub time. As I like the tree this year, you'll be in a tub. Oh, it's hot tub time. It's Christmas time. And so no upset news, it's my 12 time. Some people like to go skiing in the snow, but this is much better than that. So grab your bathrobe and meet me by the door. Oh, it's hot tub time.
So what you heard was a new song completely generated from a model. Our model was only provided the name of an artist, Frank Sinatra here, a genre, classic pop, and the lyrics to the song. It produced the whole song from scratch. And it produced this directly as a waveform with all the instruments and singing and everything included in this. Here's another example of a very different genre of music that was produced from a model.
Why do we call it a hamburger if there's no ham in it? Why do we call it a hot dog if there's no dogs in it? I don't even care 'cause I'm so as I'm back. You may break it, and I think I should be. It doesn't matter, looks only when she's ready. And I look pretty for years, and oh man, don't forget there's a really kind of spot. But when you know you want to go, clear it up.
So as you can hear, that sounds amazing, and thank you. And no other AI model that's out there can currently produce songs at this level of detail and coherence and diversity. And this is just now, as Chris said, like the ideas have been out there. We've been working on this for years, and I'm also super excited to see what will be out there like a few years of progress from now. Maybe we'll reach human level quality of music. This is the power of neural networks and the field of generative modeling right now, which I'll be talking to you today. So let's maybe first talk a bit about our motivation here. Why do I and OpenAI work on generative models? Humans are surrounded by a vast amount of data in a variety of domains, like visual, audio, text, and our brain is always trying to make sense of this vast data, constantly building better predictive models that power our intelligence. And to build very general intelligence systems, we need to do the same. The hypothesis of this field of generative modeling is that the best way to model all the data that we see around us is to try to produce it, because only then would you have understood all aspects of that data. And I think nothing better captures this than the following quote by Professor Richard Feynman: "What I cannot create, I do not understand." A model that can generate all the nuances of a data distribution must have a really good understanding of it, and it'll provide us really good building blocks for building intelligent systems. And there's been a tremendous progress in the last few years in generative modeling, in this field of generative modeling, especially using neural networks. Only a few years ago, we had algorithms that could, produce blurry looking faces, but now we can generate high resolution, like faces of people that are indistinguishable from real ones. And this is like progress over just like 5 years. On the language side, you can have models that can be trained on the entire internet to generate language like humans. And then it can be shown like a few examples of poems in a particular style, and the model will be able to generate amazing new poems in that style. This is the recent GPT-3 work from OpenAI. So why music generation? I think making music is an amazingly complex art. It's common to human culture since ancient times, and it might even predate language. More important, it's a very creative task, and so it's very natural to ask, like, can computers ever learn this creative process? And that interested me a lot, and I wanted to start working on it. So how do we go about generating music using AIs? Well, one way is to express music symbolically, kind of like text, like in a piano roll. So it looks like this. You see on the x-axis as time, on the y-axis are the notes in this picture. And at any given moment, if you want to express what is being played symbolically, you can tell what note to play, how long it is played, so kind of the length of the bars you see in the picture, what volume it's supposed to be played on, what instrument is used to play the note, and some extra parameters that kind of specify how you went about playing it, like attack velocity and so on. So this piano representation, captures a few instruments really well, like the piano, but it becomes much harder to express and generate music symbolically the moment we expand to all the instruments and all the varieties of sounds like musicians sample and play. Even capturing the exact timbre of an instrument, the nuances of how a particular person might play the guitar or the saxophone or the instrument, and the effect, even the effect of the recording space in which the music is played and so on. It's like all these nuances are really hard to express in the symbolic format. It's kind of like if you wrote down a piece of text and you compared it to the speech of a person giving it, like there are so many different ways one can say the same piece of text. So different approach would be to model music not in the symbolic way, but directly as just like a waveform, a raw audio waveform. And any piece of audio can be represented like this. Working in this space gives us the power to represent any kind of musical sound. We are not restricted to the specific symbolic set or a specific set of instruments that we can render in a symbolic way. And so we decide to work in this domain, expressing music directly as audio. And past work in this field has generated music of up to like 30 seconds from a restricted set of instruments. But in our project, we wanted to like push the boundary. And so we aimed to produce coherent music of like length up to like 4 minutes, like a song length piece of music at high fidelity and high diversity of like kinds of music, and directly in the audio domain. Generating audio as waveforms is challenging though. because we've now moved to a much bigger dimensional space with a lot more entropy, and the model will have to learn relationships over really long sequence lengths. And so when I mean really long, I mean really long. So for example, a typical CD quality song is sampled at 44 kilohertz, where this number means that its waveform has 44,000 values per second of information. And usually each value in this waveform is expressed using 16 bits of information. So this means that a 4-minute long song, if you just multiply 44,000 per second with like the number of seconds in 4 minutes, you get a raw audio sequence that has length over 10 million, which is huge. For comparison, if you had used symbolic music and for a similar amount of length, you would have like 1,000 to 4,000 event tokens describing that piece of music. Text models like GPT use also lengths of like 1,000 to 4,000 words to like model relationships between. At the extreme end, you would have like high resolution images at like 1080p, and those have like 1 million pixels in total. So the task we're aiming for is like 10 times even harder than that. Another challenge is that humans are incredibly sensitive to like small errors in the audio domain. For example, the picture here is produced from an image generative model for producing high resolution faces. And it does make a bunch of small mistakes, like the lips aren't shaped perfectly, the collar isn't matching on both sides, but we don't perceive them super strongly. It still seems like a reasonably good, like a fake face. But in the audio domain, if you try to generate something new, like even small bits of noise could, especially in high frequencies, are much more discernible and make the process of like listening to the sample like much more perceptually worse compared to like say looking at this picture. Thus, we're faced with quite a challenging task with like this super long sequence length, like us being super perceptive to like small errors. But I mean, it's okay. I think OpenAI, we like choose to work on these problems because they're hard, and it allows us to push the boundaries of what's possible with generative models today. So what is our approach here? How do we go about doing this? One way of addressing the first problem we have, which is like the input length is super long, is to use an autoencoder. So why do we use an autoencoder? Or what's even an autoencoder first? An autoencoder consists of an encoder, as you see in this picture, that maps the input X at the left to a lower dimensional space. So it kind of like shortens your sequence, so to speak, by making it pass through a bottleneck. The bottleneck here is the red block. And the compressed representation is the Z inside the block. And then it consists of a decoder that decompresses it back from this compressed space into a reconstructed input X dash, such that the reconstruction after this process of compressing and decompressing is as close to the original input as possible. And what do we obtain from this process? What it allows us to do is it allows us to convert our like high dimensional raw audio inputs to a low dimensional space by discarding some of the perceptually irrelevant bits of information. And what bits are relevant to keep is decided by the choice of our reconstruction loss, the loss between the loss that compares what goes in as input and what is reconstructed from our autoencoder. Once we've done that, once we've trained our autoencoder, we can then train a new model, a generator, to directly generate audio in this compressed space. So the space of the Z in the bottleneck. And then because of the equivalence between generating in the raw audio space and generating in this lower dimensional space, which comes from having trained these encoder decoders. And once we have the generator that can generate in this lower dimensional space, we can map it back to our original raw audio space. Oops, did I lose? One sec. Is my video back?
Oh, just now, yep.
Okay, cool. Sorry about that. And so once we've trained both the autoencoder and the generator to get back new music in the audio space, you would generate from the generator into the compressed space and map it back to the raw audio space using the decoder. The specific kind of autoencoder we use is called the vector quantized autoencoder, or the VQ-VAE. It's similar to the autoencoder that you saw in the previous slide, except the bottleneck is implemented very specifically. Inside the bottleneck, it consists of a code book of vectors. So a code book of say 512 distinct vectors. And what the bottleneck layer does, it projects the features that were coming out from the encoder to their nearest neighbors in this code book. So let's say at some particular position, the encoder produced features ZE of X, then it is projected to its nearest neighbor E4 in the code book. And we can store just an entry 4 saying that, hey, the features at this place are almost like the vector E4 in the code book. This allows us to represent the encoded inputs using discrete tokens now, discrete codes. We can just say, oh, the encoding of this raw audio sequence is 1, 2, 4, 5, 7, and so on. And then we can take vectors back from the code book that correspond to those values. Oh, did I lose video again?
Yes.
No, okay. Back?
You're back.
Yeah, I think the camera was just turning off for some reason. Hopefully it doesn't happen again, or else I'll switch to a different one. Okay, cool. So this process allows us to represent our raw audio sequence using discrete codes. And to train this vector quantized autoencoder, we add 2 extra losses to our original autoencoder. One loss is to make the codebook learn the best centers for the nearest neighbor lookup we do in the codebook. And the second one is to ensure that we commit to these centers fast, that we converge. These are the codebook and commitment losses. These are like specific implementation details of the VQ-VAE. I think the bigger thing, remember here, is we're trying to take our audio sequence, map it to a smaller dimensional space of discrete codes, and we want to convert our problem of learning the raw audio to like learning a model of generating these like smaller dimensional codes. So we can extend this idea to having multiple levels of compressed codes, compressing even further as we go higher and higher up the levels. This is similar to learning a hierarchy of more and more important and abstract features of an input. The highest level can be best thought of as like containing the most important information, and at the same time it's most compressed. So when we reconstruct from that level, the input is like the reconstructed input is going to sound the most noisy. Well, okay, I think I'm just going to switch cameras. I lost what I mean by it. Give me a second. Is the video feedback? No? One sec.
The video's back now.
Video's back.
Yeah, I switched to a different camera now. Okay.
But your screen is gone, I think so.
Yeah.
Okay.
Coming back. Yeah. I also lost my tab. Share screen. Slides. Screen back.
Yeah, perfect.
Yep.
Okay. I think the camera was just losing battery or something, so it died. This shouldn't lose it, so I think we'll be fine now. Okay, so where were we? We were at training multiple levels of compressed codes using our vector quantized autoencoder. And once we've trained this vector quantized autoencoder to compress your inputs at higher and higher like levels of abstraction, we can then train a generator to generate the other way. We can train it to generate the codes from top to bottom. We generate the most important stuff first, the most important codes first at the highest level, the most compressed ones. Then condition on them to generate the next level of codes, middle level of codes, and so on. And this particular kind of architecture was described in the VQ-VAE2 paper, and it gave really good results on image generation for like image and faces compared to like competing stuff like generative adversarial networks. It was also able to capture a lot of diversity, which is important for a domain like music. So we were inspired by this architecture, and we used a similar model for audio generation. So here we have similar model that we wrote down for generating audio in Jukebox VQ-VAE. In our VQ-VAE, we again used multiple levels of compression. So here we see like the lowest level is like compress the inputs in length by 8x. The next is 32x. The topmost is 128x. At each level, we use codebooks of size 2048 vectors. So like it contains 11 bits of information at each position. So this overall, the compression rate is even higher than 8x, 32x, and 128x. What happens in this process is, so I will play the input ground truth audio here that goes into this autoencoder. At each progressive level now, when we decode from our model, you will lose a bit of information because of the compression. So the lowest level, you don't lose much. But if you go one level higher, you can make out a bit of the noise. We went one level higher again, and that the noise now is more clear, but this is also the most compressed level. And what we've obtained here by training these multiple levels is we have been able to get more and more compressed representations that are retaining a lot of the essential information about the piece of sound, like the pitch, timbre, volume, and so on. Whereas we lose like some more and more perceptual information as you go higher, but it's like compressing and reducing our problem's difficulty a lot as we do this. It's like kind of listening to like a noisier radio as like you get further and further away into like the noisy space. And before I jump into the second half of the talk, this might be a good place to stop for any questions you have so far about our approach and the problem and what we're doing. So you guys, you can just turn the mic on and ask me a question right now if you have one.
I have a question. Is OpenAI looking at, in addition to music generation, doing lyric generation automatically as well? Or are all the samples that you've provided your own lyrics?
So it wasn't like an aim of the project, but given that we have really powerful language models, we can just like try to like either fine tune them or zero shot ask them for like, hey, can you just produce some like lyrics for us? And so the first sample we played, the lyrics for that song, Hot Tub Christmas, that was actually just a sample from the GPT-2 like language model. Like it was lyrics that the model produced, not lyrics that we wrote down. But that wasn't like the aim of the project, but it's something that is easy to do with the language models.
Cool, thank you.
I have a question, I've written one. Can you characterize what information is lost at each level? And did you check the effect of the architecture of which information is actually being discarded while you increasingly compress the signal?
Yeah, I mean, that's a great question. It's kind of hard to like qualitatively describe these things. Like though the way we've set this up, you basically, and there'll be a picture in a couple of slides that shows like the spectrograms of things. Like as you go higher and higher, you lose like more high frequency information, you like lose resolution and time and so on. It's kind of harder to quantify it in terms of like what exactly is lost about the music. It's easier to think of it like what's lost in the waveform.
Did you measure, for instance, the entropy of the different levels to see if it's actually being reduced?
The entropy in the sense of like the output waveform, or in the sense of the entropy of the codes that are being stored?
Oh, the entropy of the starting from the signal, original signal, and then at each level to see whether, what the entropy that propagates all the way to the top level.
Right, yeah. So this is, one way we do this is, I mean, we have heuristics here. One way we do is like how much of the bottleneck or the level is being used. Like, what is the entropy of the codes themselves? The other way is like you just measure like some signal to noise ratio between like the reconstructed output and the input. That kind of gives you some sense of like how much of the signal, how much of the information the signal was captured, if that's what you meant by the entropy. Does that
no, I was wondering if, so you can measure the entropy. The signal is also, each code is a signal by itself. So you can actually measure just the entropy, you know, just the expectation over the log of the probability. VQ-VAE is still a probabilistic model, right? It's a discretized VAE. So I was wondering if you actually tested that. It would be interesting for me to hear the results if you have those.
Right. So one thing we did test for was like, so for each code point, right? Each code point, you can measure its entropy or its scale divergence from like the uniform at that place. And we kind of like measure this over training. And one thing we try to do is like, we observed like for the VQ-VAE architecture, if you use it directly, it kind of like sometimes loses entropy. Like what happens is like the code book collapses and the code vectors become similar to each other, or like it's not being utilized completely. And we added like tricks like random restarts, where we like randomly reset one of the code book vectors to like an encoder output, and we observed like, oh, the entropy of it was higher now. It is now being utilized more, but we didn't really use it as like a metric in any way. But we were just like, oh, if it's staying high and it's increasing over time, then it means the model is learning useful things.
Oh, I see. Thank you.
Any other questions before I go ahead?
Yeah, I have a question. My question is regarding the representation that it takes as input. That it takes like a fixed length context window, or like the whole song. And if it takes in like fixed length, then how do you get a song out of individual chunks of audio?
That's a good question, and we'll kind of get into this also later in the talk. But basically, yes, we do train on fixed lengths of audio. And we train on like fixed length at the code level. So we train on like 8,000 codes when we actually train the generative model for the codes, which corresponds to actually longer and longer lengths in the raw audio. It corresponds to like 1.5 seconds at the lowest level, 6 seconds at the middle level, 24 seconds at the top level. And then when you want to generate longer, because the models we train for generating codes are like autoregressive models, you can like kind of do a sliding window where basically you move ahead your context by like a few tokens to generate. So you can condition on basically almost all of your generated tokens, leave a few spots for like ungenerated tokens, and generate those with your model, and just keep like telescoping this process. So like you just slide your window ahead, generate a few more tokens. Now you have a new context, you slide it ahead again, and so on. And that allows you to generate longer in the code space. And while decoding, so the architectures we use are convolutional, but they are just like the wavenet architectures here for the encoder decoders of the VQ-VAE. So even if we've trained for fixed lengths for encoding and decoding, it just generalizes to longer sequences when you want to decode from the codes. So we just pass in a longer sequence of codes, and because it was convolutional, it just managed to decode it into raw audio directly. It didn't matter that we trained on a specific length.
Okay, that makes sense. Thank you.
Could you comment, if you have time, on how this relates to Sanders' approach of using VQ-VAE on raw audio?
So there's a couple of differences. One is what they tried was train a VQ-VAE on top of a VQ-VAE. So like they would train one VQ-VAE, then they would train a VQ-VAE to compress the codes of the previous level. So the information pathway is slightly different. So here the middle level sees the input directly and is trying to reconstruct it directly. In their case, the middle level was reconstructing the codes of the lower level. The other, I think, and what that causes is like there's an information bottleneck that comes from the codes that is like really exacerbated as you go higher and higher levels. So it's really harder for them to train multiple levels and keep passing information up. This doesn't have that information like bottleneck as you go through the levels, because each level directly sees the input. The second more important difference is that they used autoregressive decoders. What that causes is a similar thing that happens with VAEs, is like the decoder is super powerful. And so when you try to put information in the codes, it might end up just ignoring the latent information because the decoder can just like predict it by itself. This, like the VQ-VAE2 paper, uses feed-forward encoder decoders, and this makes it much easier to train the codes to like actually have a lot of information.
Great, thanks.
Cool, so I'll go ahead now. So we made a few tweaks to the VQ-VAE2 architecture in this. Well, one thing we did was to maximize the use of the levels, especially the upper levels. We actually used separated autoencoders and independently reconstruct the input from the codes of each level. So in the VQ-VAE2 architecture, you would actually combine these three levels and have one single decoder going out to the reconstructed output. Here you have three separate decoders. And this prevents the model from cheating at learning time by just using the lower level or the least bottleneck level, because I mean, it's easiest to pass information through that level. And if that happens, then it prevents the learning of the levels above. But if you just separate them out, all three levels just learn nicely. One other thing we changed was, and this is a minor tweak as well, in addition to the L2 reconstruction loss, we added a spectral loss to help the model reconstruct high frequencies faithfully. So that looks like a difference in the magnitude spectrograms of the reconstructed output and the input, and you penalize the difference and add that to your reconstruction loss. And when you do this, so what you see here is at the top, a ground truth raw audio, and you see reconstructions from from each level of our VQ-VAE in the first row. So from the bottom level, middle level, top level, and you see that a lot of, information is lost at each level a bit compared to the ground truth, but a lot of information is still retained in the top level, especially the high frequency stuff. In the next row, you see if you just remove the spectral loss, you lose a lot of the high frequency information. In the level below, if you just directly use the original hierarchical VQ-VAE, you're losing a lot more information down the levels. And this is just a spectrogram of like the inputs and the outputs. So now that we've trained our VQ-VAE, we have now reduced the problem to generating the codes in the compressed space. And for this, we use a sequence of autoregressive models. And we first generate the top level codes and generate the middle level condition on the top level, generate the bottom level condition on the top two, and so on. So we just break up the probability distribution over the three as PZ top, PZ middle given Z top, C bottom given Z middle, Z top. And for that, we used transformer models with sparse attention as our autoregressive models. We used convolutional ResNets to condition on the previous levels. And as I said earlier, in this compressed space, we train on like fixed length contexts of 8K tokens, which correspond to like 24 seconds, 6 seconds, and 1.5 seconds, respectively, of raw audio at each level when they are actually like decoded from the VQ-VAE. So like if we had tried to train these models directly in raw audio, 8K like context would have like corresponded to like 1/8 of a second or something, like a very small fraction of a second of raw audio. But basically by having a compression ratios be this high from the VQ-VAE, we can train on much longer temporal horizons and therefore model much longer temporal like relationships between the input. Like the top level here can see 24 seconds of context, which is really high. And after this is done, we can just sample. Just sample from the priors from top to bottom, decode using the VQ-VAE decoder, voila, we're done. And as someone asked earlier, to generate longer songs, we just use a sliding window while sampling. So now that we've trained this, we can make the model even better by like giving it some metadata to condition on. So we can give like what is the style, like what artist style or what genre you want the music to be in. You can give information like timing. You can like tell at any particular like chunk of audio where in the song it starts, how far relatively is it in the song, and like what is even the total duration of the song that is being played. And most importantly, lyrics, because like singing is super hard to model, and conditioning on the text or the lyrics makes it much easier to do so. And how do we do this? We do something super simple. We literally just train a seek-to-seek architecture where you pass in lyrics as a sequence of characters, and you generate the top level codes, the music tokens, conditioned on the lyrics, like in any machine translation architecture. It's just encoder, decoder, style, condition on the lyrics, generate the top level music tokens. And when we do so, the model, like any translation model, learns to do alignment. It learns like at a given moment of time in the music, in the audio, what is the corresponding character in the lyric that is being like sung or being used at that moment. So an important thing to note here is that the data we train on doesn't have alignment. Obviously. It is only like a piece of text describing the lyrics of the song and just the audio. There's no time information telling where a particular thing is spoken, how is it even said or so on, no information, it's just the text. So it's actually a really hard text-to-speech problem. The data set we used. So we looked at publicly available data sets like Mastro, which had like 200 hours of piano, FMA, which was like 100K songs, but it was kind of super noisy. And there were a bunch of other data sets, but it wasn't really something that we felt was like really high quality and had a lot of diversity of music that we could train on. So we scraped a new data set of 1.1 million songs with metadata from Lyric Wiki. And this metadata had like artist, genre, lyrics, and so on, and had like a wide variety of genres. And this is super important in like any generative modeling task. Like the data you train on really can like make or break the kind of like quality of outputs you could get from the model. And if you want to see what kind of outputs you're getting from not just the cherry-picked examples, but everything that we can generate from a model, you can go to like jukebox.openai.com. We have this explorer where you can like pick your genre, pick your artist, listen to the samples from our model with like different settings, and you can just explore for yourself like what it sounds like. We've released our code, our model weights, all these samples for everyone to go explore. Before I jump into the next thing, one cool thing we can do, because we train these things as likelihood models, is you can actually complete real songs. You can take an existing song, you can pass it through the autoencoder and generate its codes, then ask the model, hey, like condition on these codes, can you tell me what comes next? Like what is your best prediction of how to complete this given song? So in the next slide, there's an example video that someone made and put on YouTube by taking a bunch of examples from our sample explorer of a particular song that they really liked, and all the continuations that we generated for that song. So here's that video.
We're no strangers to love. You know the rules, and so do I. So commitments are I'm thinking of. You wouldn't get this remaining of a guy. Doesn't want to tell me how we are. Never make you understand. Never will let this rock. Never gonna let you down. Never gonna rock you. Never gonna make you cry. Never gonna say goodbye. Let you in your eye. Magic. Always a little good time. Don't want you. Now you're in your mind. Make me say
but anyways, there. So I think one of the super cool things that was happening there was it continued it seamlessly, but and also it picked up like this is like 80s pop music. It picked up the style. It picked up like all the instruments that were playing, and it wasn't just repeating things. It was coming up with new variations of the music that it had listened to. It was actually improvising in like meaningful ways on the input that it had seen and producing like interesting new variations of music. And you can listen to a few more samples in that video of like each of the continuation sounds very different, and it's like a very different take on the same piece of music. It's super amazing and cool to like see what the model like imagines of things like, hey, what would Never Gonna Give You Up sound like? So this is our work here in Jukebox, and I would like to like now talk a bit about like the limitations of the approach that we've like taken to like generate music like this. One important thing that we still think we lack is like, even though the music that we generate is like coherent, it is lacking like large scale musical structures. Like there's not like choruses that repeat, or like clear like repetitions of melodies that you can say like, oh, it's like now did a different version of the same thing it did 2 minutes back. It has song level structure in the sense like there's a clear start of the song and end of the song. It like ends it like nicely. Like it is coherent over 4 minutes, but the large scale musical structures that you would expect from someone who's actually writing a really good musical piece are like not there yet. The upsampling process that we do, like where we train multiple levels of like transformers to like generate codes at the middle level condition, the previous bottom condition, the previous to so on. This adds a bit of like noise every time. Like you cannot model the whole distribution of the conditional distribution. And so every time you add a bit more noise, and you can hear this scratchy noise when you hear the samples. It would be great to get rid of those. And the most important one, it's slow to sample. Because we just directly train these as autoregressive models, you have to actually generate one token at a time, and then generating all the levels and getting the final output takes 9 to 12 hours for just like a minute of audio. You can generate the top level faster. That's like 1/28th the time. So it's like on the order of 30 minutes to generate 1 minute, but that's still slow. And with that said, I would still say there's like a lot of interesting like opportunities ahead to like improve these models and just like the space of models, not just this particular model. One important way you can improve things is improve the inductive bias of the codes that we learned using our autoencoder. Right now, there's like a very simple inductive bias. You want to reconstruct, they reconstruct based on L2 loss, and you want to reconstruct like in the spectrogram domain, all the frequencies and so on. But that's it. Like there's not any stronger like inductive bias that is being told to the encoder decoder, like how should you learn the compressed representation, and perceptual losses on the reconstruction and any and other techniques can help this. And if you improve this inductive bias, you can have even shorter representations of the same input. You could use hybrid architectures. You can use a GAN style architecture for actually the upsampling process, because they might be better suited. And given that you don't really need to generate all the diversity when you're upsampling on the top level, the upsamples don't sound very different from each other. It's all the information is really captured in the top level of the diversity. And so the GAN style architectures for upsampling might be better. You could improve the sampling speed. And this work already being done on this in the form of normalizing flows, like stuff like Glow that we previously worked on, but like a lot more other work that's been happening recently. That's really amazing. You could also distill models, and this has been also being actively worked on. And if we can improve the sampling speeds of these models in like you can just always have this like nice process. You just train a really good model, which is the best it can at producing really good samples, and then you can quickly like convert it into a fast model that can actually be deployed and used. We'll have the holy grail. We'll have like a really good generative model for like, and if this works for lots of different tasks, we'll have like amazingly good generative models to use. And to end here, like I would like to think of like the bigger picture here. Like we can look back at our previous slide, and like we've seen like an amazing amount of like progress in like 5 years in phase generation. In like music, there's been a lot of progress since like 2017, and there were lots of models previously too. But like I like to think of this window as like, oh, you started with like generating like small piano pieces, you like generated longer and more instrument pieces with MuseNet and stuff, and then jukeboxes and even bigger diversity and even broader space of things you can generate. So like the question now is like, what is possible in 2025? Like what is stuff that we can do 5 years from now? And I'm super excited to like see what kind of like things generative models can be able to do. Maybe we'll have human quality music. Maybe we'll have amazing like GIF generating models. We could have models that, I mean, if you go in a realm further, like you could have models for drug discovery. You could have models for like generating like interesting new chemicals or so on. Like the possibilities are endless, and I'm super excited by the work in this field. And that's it for my talk. This is a collaborative work with like a bunch of people at OpenAI, Hivu, Christine, John Wook, Alec, and Ilya. And that's it. Thanks for your time, everyone. And I'll open it up to questions now.
So maybe if people have questions, they can ask in the chat and I will slightly moderate.
Oh, I have one question.
Okay.
You mentioned that you would like to switch to perceptual loss. By the way, thank you for the talk. It was fascinating, and this research is really mind-blowing and fun. This is,
thank you.
So you mentioned you would like to switch to a perceptual loss. Could you maybe give an example or some kind of a high-level directions? How would you construct one? Because when I know, for instance, I'm thinking about MP3, which took about 10 years to get it. And MP3 is, in a sense, it's perceptual loss. It removes stuff that humans doesn't really focus on. So what would be your approach or high-level directions to that?
Thanks for the kind words, by the way, about the talk. I would say that one simple way would be if there's some like high-level feature, like classification task, let's say, that you can design. Be like given a piece of music, predict a few high-level features, then just like with ImageNet, like your architectures like would generate features at some level that are like an interesting space to like take distances in. That's one way you can generate a perceptual loss, by just like pre-training on some like classification task that is very likely to generate high-level representations that are like interesting to take like Euclidean distance in. You could use some self-supervised objectives, but I haven't thought too deeply into like the exact kind of things that will work super well in designing these perceptual losses. And I think we can take a lot of inspiration from like stuff that Envision for designing perceptual losses and see if we can come up with similar ideas for audio.
Oh, perfect. Thank you.
Okay, let's go with Sajiv.
Great. Yeah, super fun. Could you say a couple words about the relative time conditioning that you used for audio? And so, you know, I'm not exactly sure if you were saying like the proportion through the piece that you're done, but if you specify an ending, for example, how clearly did it sound like an ending? Anything else? Yeah, thanks.
Yeah, so it actually sounds very clearly like the song, and for a lot of the samples. If you actually go to our sample explorer and kind of listen to like the full length songs, like the 4-minute songs, you can see like at the end, like you slowly see instruments fade out, like the energy kind of dies down and like slowly converges to like this, like the vocals back out, like it has reached the end of the song, and there's like a few like nice ending pieces. So definitely models different distributions for the start and the end, and it makes a meaningful sense. And the reason we have these like timing signals is like basically when you actually train your generative models for codes, they are like looking at like fixed lengths of like tokens, right? And that corresponds to a fixed length of audio. Now, because it has no other memory, no other history while training, it doesn't really know where this audio chunk is in the full song. And to give it that information, we add like extra information in the form of an embedding, which tells it, okay, hey, this is how many seconds into the song this piece starts in. And we discretize this information. We tell it like the fraction, like between 0 to 1, like of the song that is completed up to this point. So like if you're 50% into the song, we like embed like 0.5, discretize again the interval 0 to 1 and give it this information. And we also like, there's a difference in distributions of like shorter songs versus longer songs. So we like give it this information as well. Be like, how long was this song? Was it like a 2-minute song, 6-minute song, or so on? Again, bin this into like some discrete number of bins and give it that as an embedding information. Usually append it to like as a start of sequence token or something to the transformer that is generating the codes. So now, even if it doesn't have a full history of the song, it can kind of make like different decisions depending on this timing information near the start of a song or near the end of a song. Does that make sense?
Yeah, it does. Thanks. Because in my experience, when I tried doing relative time conditioning with sequence models and songs, the endings tend to be particularly hard because it turns out, other than fizzling out, to actually come up with a kind of a clear ending is hard because it actually tends to need to know a lot about structure in order to do it well, like writing a conclusion. So I found that was particularly hard. But yes, that's good. Thank you.
Yeah, I mean, I wouldn't say like it has mastered the art of ending or anything, right? I mean, it's mostly fade outs still, but there were a few interesting ones, and maybe I can find some samples, and if you like message me or something on email, I can like send them to you.
Yeah, great, thanks.
Thanks.
Okay, I think Jonah had a question.
Yeah, I've been really excited about these implicit neural representations like NERF and Siren recently. And just think about how those can be incorporated into generative models. So I was just wondering if you have any thoughts on that. Like they can represent like very high frequency signals to really great resolution.
No, that's a great question. I mean, I was thinking of exactly that yesterday when I saw the Siren paper. And I think one simple way that I was thinking of incorporating this was like, well, you can now change your decoders, right? To like use the siren decoder, the nerve decoders. And basically now when you're training an encoder, it's kind of trying to like do amortized like inference and be like, okay, what is the best prior or the weights of these like siren networks or something in my distribution to like start them with. And those become your latents or the hidden representations. And I mean, there's some kind of like some results on this in the siren paper for like images. And I would be curious to like try this out for you and stuff. It's an interesting approach. I'm not sure how well it would work, but worth trying, right? I mean, like the results they have on like encoding like these like a variety of different objects using just like the weights of these like specialized neural nets is like super amazing. And so I'm really excited about what happens when we try to incorporate these into like standard architectures.
For sure. Yeah, thank you.
Mm-hmm.
So I guess I had a question, which was, is this, I mean, I guess one of the themes in OpenAI is that the bigger the model you make, all of these things end up washing away. But was there any significant difference that you could notice in terms of which genres of music or styles the model was better or worse at generating? And if so, did that reveal anything interesting about the architecture?
So it definitely got better as we made it bigger. There was basically like we had trained on like 22 kilohertz first instead of 44 kilohertz. We had also trained like a smaller, like a 250 million model. And we could see that, okay, it was harder to tell the differences in like genres. I think that was more a function of the data distribution we trained on, but it was easy to tell in terms of like how many voices can it generate? Can it generate like clear singing and so on? And the smaller models wouldn't be able to generate singing easily. They just didn't have enough capacity to model like phonemes and singing and so on, or like make it out from like such a complicated data set. But the bigger models, even when not conditional lyrics, were making singing happen. They were like, even though they didn't make sense in English, the phonemes kind of like sounded like realistic, like, oh, this sounds like human babbling something. It doesn't make sense, but it has learned to sing now, which was kind of interesting to see as we made the models bigger. In terms of genres themselves, I mean, hip hop was harder, but I don't know if it was harder just because of the capacity of the model, or just because like it's like it has this like fast pace to the lyrics, which is like really hard to model. I think genres like heavy metal were kind of easier, but maybe also they were easier in the sense of like when the model was making mistakes, it was harder to notice them when we listened to it, because they would just end up sounding like scratchy noise or something and would just blend right into the genre. So I don't know if there's like genre specific like architectural or like choices that were like, we didn't really explore it in that way, right? We were just thinking of it as like, well, as a very general setup. Does that kind of answer your question?
Yeah, I guess the thing that I had in mind is when I did this like a super baby toy version of these ideas, not these exact ideas, but worked on music in 2011. The big problem was we were working on classical music, and classical music has a lot of hierarchical structure. It's not just kind of the toy, you know, you have to remember long distance dependencies. These dependencies happen at many different levels of abstraction, basically. Mm-hmm. And I think this was the core of the problem, which might be related to why when you don't condition on lyrics, you get kind of babble, which is that music has this kind of hierarchical structure. And if you don't get that right, you end up getting music that drifts, where it sounds right. Locally very high quality. It sounds somewhat realistic, but if you consider the whole piece, it just starts kind of falling apart. Mm-hmm. And so I was wondering if you know, obviously, as you get better at matching the data distribution, these things start disappearing slowly, but right. There were sort of more comprehensive ways to think about that you guys explored.
So one way to do that would be, yeah, I mean, it definitely drifts, right? Like that was kind of what I was alluding to when I was talking about the limitations. Is like the large scale musical structure is still missing. Like locally they sound great, and there's like it kind of still has the same style and everything in the full song, but if you like really think of it musically, like, oh, it didn't make sense, what it right? It's kind of like drunk writing the music or so on. And so one way you can like help kind of hold this together would be if you just if you go back to a hybrid approach between like the symbolic and the audio, like you generate like some symbolic representation of the music first, which might not have all the information, but is already a super strong kind of like conditioning or holding together signal. And then you can now generate your top level tokens condition on that and so on. And we kind of like started doing this near the end of the project with like generating first like the MIDI tokens corresponding to like popular like pop music, and seeing if we can generate the raw audio, the top level tokens for those condition on the MIDI representation, because that's much more likely to hold it together. Still preliminary work. I think like it's an open problem there, but I think that's one approach. A different approach is what I was alluding to when I said like you can learn better inductive biases for the top level codes. So if you can somehow add some perceptual loss or even some very specific loss to the VQ-VAE itself while it's training, that kind of forces it to learn better codes, better match like musical structure. And I think this is much more challenging and harder. Then again, it's more likely when you generate or sample that you are kind of like not like the noise is because there's lesser information now, you've like actually made a more meaningful top level representation. It's less likely that you will see drift. But again, this is like a hypothesis. Like, you know, like it's hard to know if you can even like get much better codes, or like if that is the real issue here. But yeah, I mean, open problems, and I would love to see like what happens in like a few years from now. And worst case, you just wait a few years, have a lot more compute, have bigger models, and if you can just learn the distribution better, as you said, a lot of these things will go away.
Okay, yeah, great. I think that's the time. So let's thank Prafull. I guess we can all clap with our little reactions.
Thanks.
And thanks for coming, everyone. And I just want to reiterate that he's available to chat today. So if you want to kind of have follow-up questions or dig deeper into these topics, you can email him. I've put his email into the general channel on Vector Slack, and I think it's linked in the chat. So thanks for the great talk, and we'll see you around. Thank you, everyone.
Thank you. Thanks for having me. Nice seeing you.
Thank you. Super fun.
Thanks.
So we can set a time to meet if you want. Have you gotten a flood of emails, or do you still have?
I haven't checked. Right, I was
okay.
Still recovering from
the talk.
This
talk
and
was cool.
Thank you.
And getting up at 7 in the morning.
That was definitely the hardest piece of all of this, because I slept at like 3. I was like making slides at night. I procrastinated the whole day trying to make these, and then I was like, shit, it's night. I need to make these. So I have like 4 hours of sleep. So I hope I don't look sleepy.
No, it was great. It was great. Yeah. Someone. At some point I went, and I was on one of these Zoom meetings, and again, this was during NeurIPS, and I had only gotten like 4 hours of sleep or something, and I apologized, and someone said, "Oh, we didn't notice," which I'm not sure if that's like an insult or a compliment, right?
Yeah. I mean, what we can do is like, maybe we can have our chat now, and I can like reply to people and like schedule like after hours, like half an hour from hours. Okay, so let me just quickly go in order. Please visit whatever. Okay, so I'll put them at what are you? Channel. And then I will put this to 10, and then one more. Okay, cool. So
cool.
Yeah, thanks for having me.
Thanks for accommodating the East Coast time. So yeah, this is super cool work. So I guess, let's see, I had a couple of questions. So I haven't like read it closely, so you're just gonna have to forgive me for stupid questions.
It's fine, go on.
How much did you try this on like really serious classical music, or is there just kind of not enough?
We didn't try too hard. I mean, at the start, actually, I was thinking of this more as like, we have, you know, the outputs of MuseNet. Can we just reproduce like similar quality stuff, but in raw audio directly? But then at some point, we just like, by chance, we just happened to have like some like pop and rock music, and we tried it, and it was like, wait, it actually works on like real music. Like that's kind of crazy. So we just ended up steering in that direction more. And also it's like it's tilted in its favor in that domain, right? When you go back to classical music, you might like you probably actually still might want to just generate it directly in like MIDI as like symbolic, right?
Right.
Like, I don't know how much you actually lose in that.
That's
space.
right.
And I don't have a strong musical background, so I wouldn't like be like, oh, like they played that note in this very specific way, or like the dynamics of the piece. Maybe like orchestras would be something, that would be harder now to like capture so on. But like I would have personally felt like, how much are we actually losing for that if you just use MIDI? Like what do you think? Like
I totally agree, because I mean, especially if it's like a piano piece, right? Then the distance between MIDI and the raw audio, you could almost cover just with a synthesizer, right?
Right.
I mean, that is the point of MIDI, right? That's why MIDI was invented, because you can do that for classical music, and where it's much harder for other forms of music. So yeah, I definitely sympathize with that. I guess that's kind of what makes classical music so hard, because it is really all about the discrete structure. It's not as much about kind of the softer stuff. And I see. So, okay, that's cool. Yeah. And then I guess the second kind of question I had is, so I also have not been following the VQ-VAE stuff, mostly because I think it's heretical, even though it seems to work pretty well. It's fine. You should not be a zealot like I am. So, but I guess so and my understanding is that it's this just basically like greedy training, and then you learn the latent code distribution after the fact.
Oh, actually,
or is it all happening?
One quick thing.
Yeah.
I think I might have told people times for the meeting, and I just realized they are in San Francisco time. Oops.
Oh, okay. Yeah, that's okay. It's okay.
Sorry. I don't. PST. 9:30 a.m. So I think. Make sure I've told them. 10:30 a.m. Did I follow up correctly?
Take your time. Don't worry. It's not I'm not in any particular rush.
Yeah, I just realized I just send them 9:30, and then the question was 9:30 p.m. EST. And I was like, it doesn't make sense. Okay, I see what the confusion is.
Yes.
So 30 minutes from now. So okay, cool. Okay, back.
Okay, cool.
So
did I remember that correctly about VQ-VAE, that you basically have some greedy training, and then you learn a latent, and then you learn it, I guess then you sort of learn the prior post hoc over the codes. Is that right? Right. Is that still the essence of what you guys are doing, but then it's just a hierarchical version of this thing?
Yeah, we're still separately training. And I mean, a part of the reason to separately train is it's computationally better, right? Because if you actually the VQ-VAE is fast to train, is like much smaller models.
Yeah.
Right. But the priors are super big and like expressive and expensive. So you do not want them to be part of training your codes. And training it separately also just like helps you just like pick and like basically like abstracts them away. Now you have fixed this and you can like plug and play new top level priors and so on, and it doesn't matter, it doesn't change. Well, some might say that seems kind of hacky, right? Like technically, like if you think of it from a VAE perspective, to learn like good like latent codes, you want to actually learn them together with the prior, right? So you can it gets signal on like, oh, I need to compress this first. But it's kind of like a separation of concerns here. I think like you want to separate like the compression that comes from like losing like irrelevant bits, like what is provided by the choice of your reconstruction loss. Like that tells you, right, what are the bits you can like noisy things that you can forget. And you want to separate the compression that comes from like predictive coding, like what is the next most likely distribution of the next thing given the previous one. And I think the separation of concerns is a nice like computational aspect to it. Like you can like train really big models for the predictive part and really like tiny models for like the perceptual like downsampling part. But that is still hacky. Like I would still prefer if you had just one single model that can like learn to model the target distribution, has the right inductive bias so that it can separate out like learning likelihood at different scales. Like I think the key way to think about it is like you're kind of like factorizing the problem of learning likelihood into like 3 levels so that it can't cheat, right? Because when you actually just train autoregressive models directly, what happens is they focus on like the smallest n grams that they can first model, right? So they'll model 1 grams first, then 2 grams, 3 grams, and so on. And there's so much to extract in just like your small n grams. You never get to like long scale structure until like really far into training. Whereas if you just separate those concerns again into like 3 separate models. Now the top level, well, it can't even model like super fine grained structure. It can't see it at all. It only sees it at the highest level. So it has to focus on its capacity on modeling high level structure.
Right.
As the lowest one can focus on its capacity at the low level structure. So it's kind of like a different asymptotic path to like the same like likelihood maximization thing. So I would look at it like that, but it's still hacky. Like I wouldn't personally prefer this kind of model as like the best way forward for the future.
So, but I guess my question is like, do you know, because I haven't been following this area closely, I'm kind of confused. It's likely that I've missed it because I guess the questions I'm asking are kind of obvious, but basically I didn't understand when it first came out why, sorry, I just want to check, is Teju Med? I'm not sure, I'm sorry, I don't know how to pronounce your name, but are you waiting for a meeting or?
Oh.
This other, someone else's, I guess it doesn't really ultimately matter that much, but I guess we can use this room. You can keep using this room. Is that, maybe I'll message Yasmin and say, okay, so, right. Is that like when Aaron came out with that paper, it was both, like there was a lot of architectural innovation, right? Like, that was kind of orthogonal to the topic of whether it's trained as a VAE or not. Because you could kind of take the basic architecture and tack on some VAE losses, right? Basically, you would inject noise into the encoder, tack on a KL, and have to deal with the discreteness somehow, right? Like, I guess you could do a sample instead of a selection process, right? When they select the code word, you could do that could be a sample instead of a selection,
right?
If I understand the architecture correctly. And I've always kind of wondered, like, what if someone had, like, do you think that that's just going to be worse, and there's something special about the VQ-VAE training, like, algorithm, or is it more the architectural innovation that explains most of the advance?
I do think it's more architecture than like the specific way you train the codebook. I do think like the choice of like your wavenets like matters here. The choice of like downsampling small sized models, and like the real thing here is like, oh, this is quick to train, gives you like some like reasonable discrete codes to work with. And how you exactly learn those discrete codes in the codebook, like we don't actually even end up using the codebook loss, right? We do an EMA. Over things, and like there was a paper that was doing like expectation minimization, like maximization, like it was using ENM for like, oh, now you can actually think of it as like a distribution over the code words that you're outputting, and then optimize this like in a more correct way. But I don't think it actually changes much of the like results in terms of quality of like reconstructions or like the entropy of the codes. Maybe you increase the entropy of the codes slightly or something.
I see. So it's only slightly better. But even if it's better, it's usually not worth the extra cost, essentially. Okay.
That's my current like understanding of things.
Yeah. That's how deep learning works, sadly. But yeah, okay. Cool.
What are you currently interested in or like looking at, or like what do you think are exciting things happening right now?
I mean, I'm super excited about, we just posted this paper on Archive that I'm pretty excited about. It's basically a generalization of the Gumbel softmax idea. And the setting that you can imagine is basically, suppose you, okay, so the Gumbel softmax, okay, stepping back, the Gumbel max trick is a way to reparameterize sampling from a one-hot categorical distribution. And then the Gumbel softmax basically softens that sampling process so that you can get these reparameterization gradients. But like sometimes the discrete space that you're interested in might be too big to enumerate in a one-hot embedding. Okay, so for example, if you're considering the spanning trees of a graph, you could enumerate all of the spanning trees, but there are too many of them, right? It's like worse than exponential. And there's too many spanning trees. And so you might think, well, okay, I'm gonna come up with a more efficient structured representation of spanning trees. And you can do that by having a vector that is the length of the number of edges, where each dimension is just a bit that tells you whether the edge is in the tree or not. Okay, so that's like a structured, more efficient representation of trees. And so the whole idea in this generalization is to say, well, you can basically come up with the Gumbel softmax trick style idea for these structured distributions. So distributions over structured embeddings. So things like spanning trees, like k-hot vectors. So, you know, for applications with things like subset selection or unsupervised parsing or things like this. And it's kind of a combination of things that have been floating around in the literature recently. So one is this perturbation model framework, which generalizes the Gumbel max trick. And the other is this idea of kind of continuous approximations of basically linear programming solutions. And that captures, it sounds like extremely boring in a way because linear programs are like extremely simple, kind of, but this actually captures a huge set of possible computations. So things like sorting, ranking, spanning tree, maximum spanning tree, you know, matching, shortest paths. All these things are basically linear programs over admittedly like hideous polytopes. But the point is that, you know, you can design relaxed versions of those computations.
Which you can then optimize for
through which you can take derivatives. So I just think of it as this like, basically it's like expanding the set of things through which you can backprop. And so there's been a lot of people working on this stuff. The main groups, I think there's like Zico Coulter's group has done a lot of this stuff. I guess Stephen Boyd is kind of doing this stuff because it's kind of reviving convex optimization for deep learning. There's some group in France, the Google Brain group in France is interested in this kind of stuff as well. So I don't know, I'm just kind of excited about it because there's a lot to learn, and you know, I just sort of generally feel like if we expand the set of things through which you can take derivatives, it just helps people be more creative. And might be a way of kind of either imposing structure that we think should be there or we want to be there, even if it hurts performance, for example. But maybe it's a kind of just expanding the space of sort of inductive biases seems like a generically valuable thing to do. So that's what I'm kind of currently excited about.
So that's super cool. I mean, the first thought I was having, like if you can optimize all these things, maybe you can like discover like, you know, like there's problems which we are like supposed to be like super hard if you like try to solve them exactly, right? But like maybe there's, I mean, we know for a fact that approximate versions, like approximate algorithms can get really far, get really well. And a lot of the times the design of these things are very like heuristic, right? It's like we come up with some approximate algorithm that we know that we can solve the traveling sales, like kind of solve the traveling salesman problem, or like start solving in like practical instances much faster than like the worst case thing. And if you can just optimize it for practical instances, right, by training on them, then you can just like maybe get much faster version, which is like much more practical than like whatever complexity theory bounds tell you about these things, right? So that's already amazing. So the way I was thinking, and I guess the best thing for me to do is actually just check out your paper. But I was thinking, what the two difficulties, I guess, when you run into when you do this would probably be that, oh, like now you're sampling like multiple things at the same time, and you have like it's not a one-way thing. And the second would be like what you normalize over, right? It's probably the harder thing, right? To like deal with the gradient of like, so like when you are normalizing over like, let's say all kinds of like a specific discrete structure, right? You would have to now correctly do your probability like the gradient over like not just your sample, but like its relative like probability with respect to all the possibilities, right?
Yeah, so there's kind of two parts to this question. The first one is, the setting that we imagine is you're interested in optimizing the expected loss over a sample from some distribution over this discrete space, okay? That's like kind of the generic setting that you're interested in. So you could imagine just, you have some parameterization of a distribution over spanning trees, you sample a spanning tree, you compute the loss on the spanning tree in that, whatever that representation is, and then you hit it with an expected value. That's kind of like the setting we start out with. And then what we say is that, well, essentially we consider distributions which are efficient to sample from, that can be reparameterized as random linear programs. Essentially, it's distributions whose sampling process corresponds to sampling a random utility vector and then solving the linear program with that utility vector, random utility vector, over whatever polytope describes that class of objects. So for example, in the spanning tree case, it would be like sampling a random number for every edge in the graph, and then computing the random maximum spanning tree that corresponds to that random labeling. So we already start, and like one super sensible question to ask there is like, can you capture an arbitrary distribution over spanning trees? And the answer is sort of no. The only case in which you can do that is basically the Gumbel max trick, but you have to pay the cost of like exhaustively enumerating the space.
Right.
So that's the first step where you have to kind of pay a cost, which is that you can't capture any distribution. I mean, you can capture some pretty interesting ones, but okay, so that's the first bit. And then the second bit is like, how do you then relax this random discrete object into its polytope in the same way that the softmax does that? And we do that, we just basically kind of provide a generic formula where you have to basically you make a choice, which is you choose a regularizer that pushes the solution into the polytope. And an instance of that is basically marginal inference. So there's a lot of words going on here, but basically like the notion of the softmax can be generalized to these structured spaces, and that corresponds to marginals. And in that case, there's a lot of literature on computing those efficiently, despite them being, as you said, kind of normalizing over exponentially large spaces. Sometimes there's algorithms for doing it efficiently. If you can't do that, then there are other simpler choices that might be worse relaxations, but are also decent enough. So those are really good questions. And essentially the answer is you don't get something for free. You have to be able to do something like that.
Right. Okay. That makes sense then.
Yeah.
Thanks. That's pretty cool. I'll definitely check it out. I think my background in linear programming and stuff is not super well, so it's cool to learn new things.
Yeah. We tried to make it somewhat approachable, but honestly, we struggled. 8 pages is definitely not enough, and but yeah, I'm also interested in like practical compression. This is something else that I've kind of been getting into, and one of the things I want to understand, which might get a little bit, it'd be interesting to get your take on, is if you think about actually, this is a higher level question. If you think about generative models, and you say, okay, let's say I care about what I could do in principle using that model to compress data, then the likelihood is the like gold standard score, right? And so let's just say we've bought into likelihood, and now we're comparing basically like VAE style models, like latent variable models versus autoregressive models. And I love latent variable models just because I like the algorithms that operate on them, but I can't really come up with like a coherent argument that says you should be using latent variable models, because it just feels to me like whenever someone puts, throws down the gauntlet and says like, here's my latent variable model, it gets a good likelihood, Aaron is just going to show up with like DeepMind compute and come up with some ridiculous architecture and scale it up, and it's just going to crush your latent variable. His autoregressive model is going to crush your latent variable model, because at the end of the day, they can just like write down the likelihood. There's no approximations. There's nothing else. It's just like deep learning, fair and square, right? Just like full blown. You increase compute, you write down your likelihood, and you just do better, right? That's it.
Right.
That's the formula. So, do you have a defense of latent variable models? Or do you think that what I just said is basically right?
I don't want to say this, but I do think what he said is basically right.
Yeah. Okay. I know it's right. I just don't want it to be right.
I feel like, what could be? What we did is a latent variable model, right? And
that's why I want you to defend it.
Yeah, my defense is from a practical notion. I wouldn't say the defense is from like a fundamental or like, oh, there is some like fundamental like improvement you'll get. If anything, if you just can directly optimize, you would always be better. I do think the practical notion, at least in this case, was, as I said, you can like separate the concerns of your likelihood model now by having different levels of latent representations that are like focusing on different aspects of the input, so that you don't end up allocating capacity to just like one specific thing and overfit to like one specific kind of like correlations in your like, the final structure, because now you have like separation of concerns in your likelihood model. That's one reason, and that also has efficient compute allocation now, because you can like train on different, like on the same batch sizes, but at different scales at the same time. This is like a very practical like argument for like why to have a latent variable model. Like, I don't know. I don't know if humans have like internal latent structure or something. I do think a lot of what is probably happening with us is like you have like your input streams, and so on. There's some like pre-processing, some like trivial like downsampling that's happening right at the input stream, and they just all feed in as like signals into your brain, and your brain is just like, well, given all these signals, what's my best model of the signals like 1 second from now or something, like whatever is the time step at it. And I don't know if there's space for like special latent variable models or anything. It must be like implicit in the predictive model.
So you think we're just like really just a giant autoregressive model soup? Well,
that's the most simple and attractive model to me.
I think you're right. I think it's good if you have a good practical. I guess the other thing which you'll probably have a better sense of is like, how realistic are the like decoding time concerns? Like obviously autoregressive models, the naive implementations are extremely expensive. And I know the WaveNet guys put a huge effort into making these things practical. And do you think that those are realistic concerns, or it's just like enough clever engineers at Google can solve it for our purposes?
Yeah, I actually think it's not too big of a concern, right? I feel like there's already established like ways of like, well, you can like distill it maybe into a fast sampler. Maybe you can just like engineer the heck out of it, as they did with like the like speed generation stuff, so that it's like now the latencies of your kernel calls are like super low, and like it's actually like pretty fast. Like really, it's not like they are slow, right? It's just that they don't utilize GPUs well.
Yes, right.
Like the amount of flops that it actually takes is actually reasonable.
Yeah.
The problem is the way those flops are structured is not reasonable with respect to the GPUs that we have right now. I don't think that's really a fundamental issue, right? That's like an engineering issue. Plus, if flows ever work out to end up being the replacement for all of these things, then it would be like amazing. It has its own issues with like, oh, like these models become more complicated, much bigger, and you still can't match the same levels of performance as your direct autoregressive models. But if that line works out, then that would be amazing too, right? Then you just get fast sampling for free. So I don't think of it as like too big of a deal.
I see. Right. So it's just if you're for your specific data, you have some practical reason to believe that this separation of concerns is important. That's kind of your like your kind of hierarchical jukebox argument.
Mm-hmm.
Yeah. Okay. Cool. I think I guess people are going to file in here. I'm assuming that that's what's going to happen.
People sent me like links to like join or something, so I'll just like switch to those links and stuff. But it was great chatting.
Okay, so just ping me if you need anything, or ping Yasmin, and we'll set up another Zoom room if something fails. Okay.
Okay. Cool.
Okay. Cool. See ya.
See ya.
Bye.